in the absolute void of space, where temperatures swing from searing heat to unimaginable cold, where radiation tears through matter unshielded by atmosphere, where pressure drops to near nothingness and water boils away in an instant. Nothing should survive, not bacteria, not fungi, not the hardiest extremophile clinging to hydrothermal vents, and certainly not a creature barely visible to the naked eye, a microscopic animal with 8 stubby legs and a face that looks almost comical under magnification. Yet the tardigrade does not merely survive the vacuum of space. It enters a state so profound, so alien, that it borders on death itself. It shuts down. It waits. And when conditions allow, it wakes. Today, we're unraveling one of biology's most bewildering enigmas. Why an animal no larger than a grain of sand has evolved the ability to endure the one environment Earth never prepared it for. This is not about toughness. This is about a biological strategy so extreme, so counterintuitive, that it challenges everything we think we know about the boundaries of life. The tardigrade, often called a water bear or moss piglet, lives in places you would never think to look. In the thin film of water-coating moss, in the droplets clinging to lichen on a rooftop, in the damp leaf litter of a forest floor. These are not extreme environments. They are ordinary, mundane, forgettable. And yet, the tardigrade's evolutionary history has carved into its biology a survival mechanism designed not for the moss, but for annihilation. It is called cryptobiosis, a state of suspended animation so complete that metabolism stops entirely. The tardigrade does not slow down. It stops. No heartbeat, because it has no heart. No breath, because it does not breathe in the way we understand. No cellular respiration. No energy consumption. No aging. It becomes a biological artifact, a capsule of potential life, waiting. But why? Why would a creature living in a puddle of water on a patch of moss need to survive the vacuum of space? The answer lies not in space, but in time. The tardigrade's habitat is not stable. Moss dries out. Puddles evaporate. Lichen bakes in the sun. For a tardigrade, these are apocalypses. The water that sustains it vanishes in hours, sometimes minutes. Without water, cells collapse, proteins denature, DNA fractures. Death is immediate, unless you can stop being alive in the traditional sense. The tardigrade evolved cryptobiosis not for space, but for drought, for desiccation, for the everyday catastrophe of a disappearing water film. But the mechanisms it developed, replacing cellular water with Trehalose sugars, forming a glass-like matrix inside cells, retracting its legs and curling into a barrel shape called a ton. These mechanisms happen to protect against far more than drying out. They protect against radiation, against freezing, against boiling, against pressure, against the vacuum. The tardigrade did not choose space. Space is simply within the boundaries of what cryptobiosis can endure. In 2007, the European Space Agency launched the Photon M3 mission. Among its cargo were tardigrades and thousands of them, dehydrated, in their ton state, packed into small containers. The mission exposed them to the vacuum of space, to solar radiation at levels that would liquefy human tissue, to temperatures oscillating between extremes. For 10 days, these animals floated in orbit, subjected to conditions no terrestrial life should withstand. When the capsule returned to Earth, researchers rehydrated the tardigrades. And they woke. Not all of them, many did not survive, but a significant percentage resumed normal activity. They moved, they fed, they reproduced. The ones exposed to vacuum alone fared better than those exposed to vacuum and full solar radiation. But even some of those survived. This was not an accident. This was biology functioning at the edge of what chemistry allows. What happens inside a tardigrade during cryptobiosis is still not fully understood, but the pieces we have are astonishing. When water disappears, the tardigrade begins producing massive amounts of trehalose, a sugar molecule that essentially replaces water in the cell. Trehalose forms hydrogen bonds with proteins and membranes, stabilizing them in the absence of water. The cell does not collapse, it vitrifies, turning into a glassy solid. DNA, normally vulnerable to breaks and mutations, is protected by proteins that coat the strands, preventing damage. The tardigrade also produces unique proteins called tardigrade-specific intrinsically disordered proteins, or TDPs. These proteins have no fixed structure. They are molecular chaos, and that chaos is their function. They form a web inside the cell, a flexible protective scaffold that cushions organelles and macromolecules against physical stress. In this state, the tardigrade is not alive in any metabolic sense. It is a molecular time capsule, biochemically locked, waiting for the return of water. But the vacuum of space adds layers of threat that desiccation alone does not. In a vacuum, pressure drops to nearly zero. Gases dissolved in tissues, oxygen, nitrogen, carbon dioxide, want to escape. In most organisms, this causes embolisms, ruptures, death. But the tardigrade in its ton state has no active circulation, no gas exchange, no fluids under pressure. There is nothing to boil away because it has already removed the water. The glassy matrix holds everything in place. Radiation is another matter. Cosmic rays and ultraviolet light damage DNA by breaking the double helix, creating mutations, triggering cell death. Tardigrades exposed to radiation in space show DNA damage, but they possess repair mechanisms of extraordinary efficiency. Proteins like D-subdamage suppressor bind to DNA and physically shield it from radiation. When the tardigrade rehydrates, repair enzymes go to work, stitching together broken strands, excising damaged segments, restoring genetic integrity. It is not perfect. Some tardigrades die. Some carry mutations. But enough survive to reproduce, and that is all evolution requires. The temperature swings in space are brutal. In direct sunlight, surfaces heat to over 120 degrees Celsius. In shadow, they plummet to minus 150 degrees Celsius or lower. Proteins, the machinery of life, denature at high heat and crystallize at low temperatures. But in the vitrified state, tardigrade proteins are locked in place by trehalose and TDPs. They cannot unfold. They cannot crystallize. The glassy matrix is thermally stable across a range that would destroy most biological material. In laboratory experiments, tardigrades have survived being frozen in liquid nitrogen at minus 196 degrees Celsius and heated to over 150 degrees Celsius. They have been subjected to pressures 6 times greater than the deepest ocean trench, and to near vacuum conditions. They have been irradiated with doses thousands of times higher than what kills a human. And still, when conditions return to something approximating normal, when water is reintroduced, they wake. This raises a deeper question: is cryptobiosis a kind of death? Philosophically, biologically, the tardigrade in its ton state is not performing any of the processes we associate with life. No growth, no reproduction, no response to stimuli, no metabolism. By some definitions, it is dead. By others, it is dormant. The line is blurred. What is certain is that the tardigrade can remain in this state for years, possibly decades. There are reports, though not universally accepted, of tardigrades reviving after more than a century in museum collections. Whether this is truly possible, or whether contamination and misidentification are at play, remains debated. But even conservative estimates suggest tardigrades can survive in cryptobiosis for at least 10 years, perhaps longer. Time stops for them. They do not age. They do not degrade. They wait, locked in a molecular stasis, until the universe offers them a second chance. But cryptobiosis is not unique to tardigrades. It appears across the tree of life in bacteria, fungi, plants, nematodes, rotifers, brine shrimp. The mechanisms vary, but the principle is the same: shut down, survive, restart. What makes tardigrades remarkable is the extremity of conditions they can endure in this state, and the efficiency of their molecular machinery. The TDP proteins, for instance, are unique to tardigrades. Other organisms use trehalose, but not with the same effectiveness. The DSUP protein, which shields DNA, has been experimentally inserted into human cells, and it works. It reduces radiation damage. This is not science fiction. This is real, functional biology, evolved over hundreds of millions of years in a creature that lives in moss. And yet, tardigrades are not invincible. They can be killed. Boil them while hydrated, and they die. Crush them, and they die. Starve them for too long in their active state, and they die. They are only resilient in cryptobiosis, and only then because they have preemptively dismantled the vulnerabilities that make life fragile. They are not surviving the vacuum of space. They are surviving the absence of life's requirements by ceasing to require them. It is a loophole, a biological technicality, an evolutionary hack that works, because the universe, for all its hostility, operates on rules. And if you can pause your dependence on those rules — water, oxygen, moderate temperature, stable pressure — you can wait them out. The implications ripple outward. If tardigrades can survive space, could they survive interplanetary travel? Could they hitch a ride on a meteorite ejected from Earth, drift through the void for millions of years, and land on another world? This is the theory of panspermia, the idea that life spreads between planets, even between star systems, carried by debris. Tardigrades are among the few organisms that could plausibly survive such a journey. They would not be conscious of it. They would not choose it. They would simply wait, as they have always waited, until water returns. If Mars once had liquid water, if Europa's subsurface ocean ever breaches the ice, if Enceladus's plumes rain down onto a moon with the right chemistry, could life, in the form of a cryptobiotic tardigrade, wake there. It is speculation, but it is grounded in the reality that tardigrades have already survived conditions we once thought were incompatible with any biology. We still do not fully understand how cryptobiosis works at the deepest molecular level. We do not know the limits of how long it can last. We do not know if there are environments so extreme that even a tardigrade in its ton state would fail. We do not know if the mechanisms could be adapted, enhanced, applied to other organisms or to us. There are researchers exploring whether trehalose and TDP-like proteins could preserve human cells, tissues, organs for longer periods without degradation. There are questions about whether cryptobiosis represents a third state between life and death, or whether our definitions are simply inadequate. There are mysteries in every protein fold, every sugar molecule, every repair enzyme. But what we do know is this: the tardigrade did not evolve for space. It evolved for a puddle drying in the sun. And in solving that problem, it accidentally solved 1,000 others. It became a creature that can outlast vacuum, radiation, temperature, pressure, time. It became a biological constant in a universe of variables, and in that there is something profound. Life is not about strength, it is about strategy. It is about finding a way to pause, to wait, to endure until the universe offers one more moment. The tardigrade chose nothing. Evolution chose for it. But the result is the same: a microscopic animal that sleeps through the void and wakes when water returns. And in that patience, in that terrible, beautiful patience, is a lesson we are only beginning to understand.